Hello class, this is CSE 5720, section 2, week 13, fall 2025. So, due to complications regarding the weather, I had to postpone this video until now. So, this is the video that was actually meant for last week, so really this should be week 12's video. Okay, so let's recap what we are looking at in chapter 8. So, we are looking at what makes for a good database design. We're going to review the three following things from the last video: first normal form and Boyce-Codd normal form, and the notion of a functional dependency. So first normal form is one of several normal forms for a database. Here, we require that the domains of each attribute is atomic. Put another way, if you have a table, there must be one entry per cell. If you have an address, for example, is going to be composed of several smaller attributes. We give each of those attributes its own cell. So Alice and Bob respectively live at Street, City, Town, Massachusetts, and Road, Town, City, California. Street would be in its own cell. City, Town would be in its own cell. Massachusetts would be in its own cell, and so would the zip code. Road would be in its own cell, so would Town, City, and so would California. So that means we cannot have this where we have multiple attributes within one cell. We give each one its own cell. So that means we just break up the address into smaller pieces: street, city, state, and zip code. Let's also say Alice and Bob have two different phone numbers each. Well, under first normal form, this is not allowed either. So much like how we broke up the address into smaller attributes, we would break up the phone number's cells into their own cells. Except the phone number is only one attribute. We would instead give each of these phone numbers its own row. So with the address, we gave each component attribute its own column. With the phone numbers, we give each phone number its own row. And here's the same information in first normal form. Oh, by the way, if you have nested tables, that's also a first normal form violation. So we have three customers named Abraham, Isaac, and Jacob. What do they have? What? These are names straight from the Bible. Is there mentions of credit cards in the Bible now? Anyway, we have three customers: Abraham, Isaac, and Jacob, and then each customer has its own transaction information. This is a first normal form violation. We want one piece of data per cell. But look at these nested tables. We have a transaction ID, date, and amount, and it's the same thing for Abraham, Isaac, and Jacob. Why don't we just take those nested tables, put everything in its own table, and then add a fourth attribute? That's the customer ID, so you know which customers have which transactions. So that's exactly what we do. We split this table from being a nested table into one customer table and one transaction table. The next thing is a functional dependency. We say that an attribute determines another attribute if, for each value of the attribute, it determines one and only one value. So if we have A determines C, any value for A determines exactly one value for C. So we have two rows in which the value for A is A1, two rows in which the value for A is A2, and one row in which the value for A is A3. We can illustrate this as such and come to the conclusion: A determines C because for each value in A, it maps on to exactly one value in C. So A1 maps to C1, A2 maps to C2, A3 maps to C3. Actually, there's no C3. It actually maps to C2. And this is okay. We have either a one-to-one mapping or a many-to-one mapping. And both are allowed when we have functions like this. What would break it is a many-to-many mapping or a one-to-many mapping. If we have that kind of mapping, we don't have a functional dependency anymore. So we have first normal form, and then we have Boyce-Codd normal form. The definition of Boyce-Codd normal form is contingent on the notion of a functional dependency. So a relation schema R is in BC and F with respect to a set of functional dependencies if for all functional dependencies in F plus of the form alpha determines beta, where alpha and beta are subsets of R, at least one of these holds. Alpha determines beta is a trivial functional dependency, that is, beta is a subset of A, or A is a superkey for the schema R. We saw also an example of a Boyce-Codd normal form violation. It is this table. So we want one of these two conditions to be met. Alpha determines beta is a trivial functional dependency, or alpha is a superkey of R. Here we have the department name, and that determines two things, the building and the budget. So each department in our university example is associated, so each department is in a building, and each department has its own budget. The department name is enough for us to determine where is this department and what is its budget. But we cannot use the department name as a superkey because in this table we have department names being repeated. And for a superkey to work, for a set of attributes to be a superkey, those attributes alone must be enough to uniquely identify every row in the table. Because we have repetition here, we cannot uniquely identify every row using the department name as a superkey. The ID works as a superkey, but the ID determines name and salary. We could use it to determine everything else, but we want the department name to determine building and budget. But for this to be in Boyce-Codd normal form, department name must be a superkey. In other words, we have to cut this thing into two separate relations, one for instructors and one for departments. And now, Boyce-Codd normal form violation gone. There is one issue with Boyce-Codd normal form worth discussing here. Say you have a ternary relationship between an instructor, a department, and a student. In our university example, we expect each student to be advised by one instructor who is fulfilling the role of advisor. However, it's reasonable to expect some students to be dual majoring. So we would expect that a student who is dual majoring in say two different majors, say computer science and music, they would need an advisor for both departments. One for computer science, one for music. What this diagram says is one student gets one advisor per department. So if a student has a department advisor, they only get one department advisor for that department. If a student dual majors, they get a separate department advisor for that department. That's also what this arrowhead is saying for this entity department. This says, this is basically what I'm saying here. One advisor per student per department. And this is what that ER diagram captures here. One advisor per student per department. The primary key for this ternary relationship is going to be the primary key attributes of the three participating entity sets. In other words, the student ID, the instructor ID, and the department name. This has an additional constraint. which I had actually mentioned already. So that constraint is an advisor can act as an advisor for only one department, which is actually what is also captured by this arrow here. If an instructor is advising, they can only advise for one department at a time. An instructor can only be an advisor for only one department. So that's what's being captured in this diagram here. So now we have these functional dependencies. Instructor ID determines department name, and student ID and department name determine instructor ID. From here, we can then have the following functional dependencies here. Instructor ID determines department, since one instructor can advise for only one department, and student and department determines instructor ID. Let's add some example data, but I am going to abuse the notation here. I'm going to abuse the schema here and just write down instructors and students' names. If I want this to be proper, I should use their instructor and student IDs instead, but just for the sake of demonstration, I am going to use their names instead. So for this instance, we have 3 instructors and 3 students across 3 departments. Instructor Einstein is advising student Snow. Instructor Brandt is advising students Shankar and Williams. Instructor Mozart is also advising student Williams. And of those 3 students being advised, Williams is dual majoring. Let's bring back our 2 functional dependencies. Instructor determines advisor holds due to our constraint where an instructor can only be an advisor for only one student. Student and department determines the advisor holds, since that's enough information to determine which student is being advised by which instructor, even if a student is dual majoring. Also note, if our dependency was student determines advisor, that's actually not enough information, because if we had the functional dependency student determines advisor, that's not enough information, because Williams is dual majoring. Williams needs 2 advisors. If we say student determines advisor, which advisor? Which advisor are we talking about? Williams has 2 advisors because Williams is dual majoring. So that's not enough information. We need to add the additional information of, okay, Williams, you're talking about Williams computer science advisor, or you're talking about Williams music advisor. Okay, now our big question is this table in Boyce-Codd normal form? The answer is no. For this to be in BCNF, the left-hand sides of these 2 functional dependencies, instructor determines department name and student ID and department name determine instructor, those 2 must be superkeys. There's actually another condition that could be met here, but that doesn't apply for this case. We want these 2 functional dependencies, the left-hand sides, must be superkeys. The superkey of student and department, is that enough information to uniquely identify each row? Einstein's no. No, actually, student physics. Yes. Shankar computer science. Yes. Williams computer science. Yes. And Williams music. Yes. That is enough information to uniquely identify each row. So the problem with this particular instance is Williams shows up twice because that's the same student. If we really want to be proper about this, as I said, we should be using their student IDs, and for the instructors, their instructor IDs. Because what if those are 2 different Williamses? That's a problem that we circumvent by assigning all students and instructors with their own unique ID. Again, the reason why I did not use IDs is because I wanted it to be easier to understand. If you can understand this with unique people here, again, there are 3 instructors and 3 students, then we can swap out their names for the respective IDs and they'll still work. So, going back, the superkey of student and department. That is enough information for us to uniquely identify each row. But if we did this with the instructor, that's not enough information. And you want to know why? Because an instructor can be an advisor to more than one student. Brant is an advisor to 2 different students. If we use the instructor as a superkey, we cannot uniquely identify each row. So the solution to this is to just cut this table into pieces. So now we have 2 separate tables, instructor and student, and another one, instructor and department. So this decomposition comes from our rules for decomposing a non-BCNF schema into 2 that are. And if those 2 schemas are not in BCNF, we can just reapply the decomposition rules again until we get a set of schemas that are in BCNF. Okay, so what about our functional dependencies down here? Instructor determines department name, and student and department name determines instructor. Well, we have the functional dependency instructor determines department name. That holds for the instructor and student table. But look what happened. We have our functional dependency student and department name determines instructor, but there is no more table for which that functional dependency would hold. So we cut this table into 2 pieces to make it into Boyce Codd normal form, but in doing so, we ended up losing one of our functional dependencies. It no longer works. This functional dependency no longer works because there is no schema that has the 3 attributes ID, student ID I mean, department name, and instructor ID. So, as much as we would like to preserve the second functional dependency, student and department determines instructor, we cannot if our schemas are in BCNF. So, this is not dependency preserving. If we take this table and made it into Boyce Codd normal form, we lost one of our dependencies. We lost one of our functional dependencies. Which makes you wonder if, okay, so is there a normal form that would let us keep the structure that we had in the previous table? That is to say, Boyce Codd normal form is too strong. Is there a weaker version of Boyce Codd normal form that we can use instead? The answer is yes, and that is called third normal form. Alright, so we talked about first normal form, and now we're talking about third normal form. Where's second normal form, you might be wondering? Well, for completeness, a schema that is in second normal form has what are called... Okay, so for completeness, I'm just going to give you the definition of second normal form. A schema that is in second normal form has no partial dependencies. That is, if a primary key contains more than one attribute, all non-key attributes depend on the entire key and not part of it. The text doesn't really talk about second normal form because the author says we don't really use it anymore. The reason I'm bringing it up is for completeness sake. When you look at different normal forms, it's building up in a hierarchy. So first normal form, and then second normal form on top of that. And then on top of that is third normal form, and then on top of that is Boyce Codd normal form. So, a schema that is in second normal form has no partial dependencies. If you have a primary key that consists of 2 or more attributes, all non-key attributes must be determined by both of those attributes, not part of it. If you have the whole primary key, you must use the entire primary key. You cannot use part of it. If a schema is not in second normal form, that means you have a primary key and one of your non-key attributes that depends on part of the key. If that's the case, you can just cut it in half, like you would with the other schemas that were not in Boyce Codd normal form. You want to see an example of what a second normal form violation looks like? I'll be right back. Alright, so here's an simple example of a second normal form violation. So, we have a table of student enrollments, basically what students took what courses and what grade they got for that course. So, we need a primary key for this table, and it's not enough to use the student ID because a student may obviously take multiple courses, and it's not enough to use the course ID because a course could be taken by multiple students. So we need both the student ID and the course ID to form the primary key. So, primary key and course ID. Both the attributes form the primary key because on their own, student ID and course ID is not enough information to uniquely identify each row in the table. So, we can use the student ID to determine what student we're looking at. So, we can then say the student ID determines name. Also, looking at the table, we can also from there infer that each student is associated with a grade, so we can also say that the student ID determines the grade. Also, so the student ID determines the name and the grade. The course ID, each course ID is associated with the name of the course. So in this example, CS-404, that is Intro to 3D Modeling, Music 311, that is Intro to Microtonal Music Theory. So the course ID determines the course name. So we can write down the following functional dependency. There we go. So, what makes this a second normal form violation is the fact that... Oh, hold on. Okay, it's actually screwed up with one of the functional dependencies. Is the student ID alone enough to determine a student's grade in a class? Actually, no, because if Alice took also microtonal music theory, what grade are we talking about? So yeah, student ID alone is not enough to determine the grade. We actually need two attributes, and that second one is course ID. So student ID and course ID determines the name of the student and the grade the student got for that course. But look at the functional dependency of course ID determines course name. Because each course ID is associated with exactly one course name, we don't need any further information than the course ID. So if that means if we are also using the student ID to determine the course name, that is actually unnecessary information. So we can use only the course ID. That means we're only using part of the primary key. That means we have a partial dependency. That means we have a second normal form violation here. The solution to that would just be to split the table into two. One table that is just the table of the student's grades, so it would just be this column. It would just be this, and this column. We don't need the course name anymore. In fact, course ID and course name can be its own table, presumably with additional attributes that tells us what department that course is in. So, this is a second normal form violation because the primary key is student ID and course ID, but the course name is only determined by the course ID. the non-key attributes of name and grade are determined by both the student ID and course ID. So there's no violation there, but we have a second normal form violation because the course ID alone determines the course name. So the solution is to just split this out to be okay, so the solution to this is to, if I can copy paste this properly, that's table number 1, and table number 2 is that. So there we go. Now these two schemas are in second normal form. So there's your second normal form violation example. It kind of feels like we just did a decomposition for like Boy Scout normal form though. And that's the thing about all these different normal forms. As I said, they form a hierarchy of normal forms. So that means each subtext of normal form actually has all the same requirements of all the normal forms before it. Also, Geeks for Geeks has summarized definitions for all of our normal forms that you might find to be a bit more intuitive than the one that the textbook gives. So, first normal form means all columns contain atomic values. Second normal form means no partial dependencies. What we're going to see in third normal form is no transitive dependencies. The text defines third normal form in a different way, but somehow that definition is equivalent to no transitive dependencies. And Boy Scout normal form is, for a non-trivial functional dependency, X determines Y, X is a superkey, or Y is a subset of X. So those are the definitions of all of our normal forms, but because each higher normal form builds off of the last, it means each higher normal form has all the requirements of all the normal forms before it. So second normal form has its own requirements plus those of first normal form. Third normal form has its own requirements plus those of second normal form, which implicitly means that third normal form has the requirements of first normal form. Boy Scout normal form is a stronger version of third normal form, which means that Boy Scout normal form has all the requirements of third normal form, and second normal form, and first normal form. So when I say third normal form is a weaker version of Boy Scout normal form, that is what I mean. By the way, there's about 10 different normal forms here. So, first normal form, second, third, EKNF, BCNF, 4NF, ETNF, 5NF, DKNF, and 6NF. We are not going to go through all of these normal forms. We're only ever going to go through a portion of these. So the textbook only goes up to like first, third, BCNF, and fourth normal form. It only ever briefly mentions second, fifth, and another normal form called DKNF. Domain key normal form, I think that's what it's called. We're only ever going to go as far as fourth normal form here. Okay, so let's look at the definition of third normal form. So recall that a candidate key is a superkey in which no proper subset is also a superkey. So a candidate key is some candidate set of attributes that you are probably going to use as your primary key. I say probably because you might have other candidates that you might choose. Or you might find out there might be some extraneous attribute in your candidate key that you might want to throw out. Because adding it does not add any new information regarding identifying each row in a table. So here's the definition for third normal form. A relation schema R is in third normal form with respect to a set F of functional dependencies. If, for all functional dependencies in F plus of the form alpha determines beta, where alpha and beta are subsets of R, at least one of these three holds. Alpha determines beta is a trivial functional dependency. Alpha is a superkey of R, or each attribute A in beta minus alpha is contained in the candidate key for R. If you look closely, you'll notice that the first two requirements are that of Boy Scout normal form. So the third condition is the new one. this will probably become more clear when we try an example. So, Boyce Codd normal form is stricter than third normal form in that it eliminates the third requirement here. So here's an example. It's our previous example of we want this table to be normalized, but Boyce Codd normal form was way too strong. This was not in Boyce Codd normal form because for the first functional dependency, instructor ID was not enough information to be a superkey. And trying to decompose it did not preserve the second functional dependency. This is to say that when it comes to these different normal forms, you gotta stop somewhere because if you kept going, you might lose some useful information about your schema. If Boyce Codd normal form was too strong, let's go back and try another weaker normal form. If it's not in Boyce Codd normal form, and we can't decompose it, is it at least in third normal form? The answer is yes. So, the first functional dependency, where a functional dependency is of the form alpha determines beta. Alpha is instructor ID, beta is department name, and beta minus alpha is department name. So, since the second functional dependency holds, department name is contained in a candidate key, so this schema is in third normal form. So that third requirement said, and we only need one of these to hold, that new requirement is each attribute A in beta minus alpha is contained in a candidate key for R. So, instructor ID determines department name. Instructor ID is a candidate key, but it's not a primary key, or rather, it's not a super key. And as I said, a candidate key is a set of attributes that we could use to identify each row. And it's called a candidate key because we might find a better key than that. So this is not in Boyce Codd normal form because that first condition would fail and trying to decompose it would result in the second condition no longer being valid. So, if we can't use Boyce Codd normal form, let's just try third normal form. So when it comes to choosing a normal form, there's going to be some trade-off. We could not preserve all the functional dependencies by upholding Boyce Codd normal form, so we backtrack and tried third normal form instead. There are some other higher normal forms, but using functional dependencies is done to reduce unnecessary repetition in a schema, but this can't always be done. So here is a table of our instructors for our university example. Let me just move my webcam a little bit. So consider what happens if we have a variant of this table, where we, in addition, we add to the schema instructors' children and instructors' phone numbers. So we're going to get into unneeded repetition here. Let's also consider a smaller instance to keep things simple. So let's say that instructor Mozart has two children named Dvorak and Joseph. Instructor Wu has a child named Vu. And also instructor Mozart has two different phone numbers. So, basically, not all instructors are going to have children, and those who do may have more than one child. Similarly, instructors may have more than one phone number. Or it might be the case that they have a phone number and it was never reported to the database. Also, it's possible that two instructors might have the same phone number. Since instructors' phone numbers and instructors' children are separate entities, it makes sense for us to split this schema into three. So now we have our original table of instructors, their departments, and their salaries, a new table of instructors' children, and a new table of instructors' phone numbers. We could combine the two tables for instructors' children and instructors' phone number into one, like this. This new schema is in BCNF, since only non-trivial functional dependencies solve. Is this a good schema though? Let's try another instance where we have an instructor who has 2 children and 2 phone numbers. So, if we tried this schema with an instructor who has 2 children and 2 phone numbers, we have a table that looks like this. You look at that and you think to yourself, wait, is David the one with the ID of 99999? And is David the one with the phone numbers 512-552-555-1234? Or is that 2 children named David? It's going to cause a little bit of confusion, but the point is, if we want each row to have if you want each cell to have its own piece of data, we're gonna have some repetition that we would like to avoid because this is a little bit repetitive. Even if we eliminated that repetition by just eliminating the 2 middle rows, now it looks like David's the one with the phone number 512-555-1234, and William's the one with the other phone number 512-555-4321. Issues like this are discussed in sections 8.6 and 8.7, which are not quite there yet, but that's just a discussion on this is more of a sneak peek of higher normal forms beyond third normal form and Boyce-Codd normal form. So, we're not quite done with our discussion on chapter 8 yet. There is another set of slides that I have to get to. And it's going to get a lot deeper than what we've talked about so far. Okay, here we are. So, we're going to continue our discussion on section 8.4, functional dependency theory. We're really getting in deep in the weeds here. So, a set of functional dependencies logically implies another set of functional dependencies if a database satisfying the first set of functional dependencies also satisfies the second set of dependencies. So, what does that mean? Well, if you have a set of functional dependencies, it's possible to create another set of functional dependencies that is equivalent to the first set of functional dependencies. That means if a data set satisfies the first set of functional dependencies, it's going to satisfy the equivalent set of functional dependencies. So let's look at an example. Suppose we have this schema here with the following functional dependencies. A determines B, A determines C, CG determines H, CG determines I, B determines H. We're going to create a brand new set of functional dependencies just from these. And we're gonna do that using 6 different rules of inference. Also, when you see CG written like that with nothing in between, that's just a shorthand for C union G. So CG is the set of attributes of C and G. So the first rule we're going to look at is called the reflexivity rule. If A is a subset of AB, then AB determines A. So this produces a statement that's automatically true, because if you know a superset, you already know all the possible subsets. If I give you a fresh pack of crayons, and not just any pack, it's a 64-pack Crayola crayons with a sharpener in the back, never been opened, freshly bought from the store. If I give that to you, do you have a yellow crayon? Of course you do. It's gonna be somewhere in the pack. Unless there was a manufacturing error at the factory, then that means I'm gonna have to go back to the store and probably request a refund or probably just get a brand new box of crayons. If I give you a fresh new pack of crayons, that means I gave you a yellow crayon. The second rule is called the augmentation rule. If A determines B, then AG determines BG. It's like when you have a mathematical equation and you multiply both sides by 2 to keep the whole thing balanced. So, adding G, unioning A with G, doesn't change the fact that A still determines B. But also, at the same time, unioning B with G doesn't change the fact that A still determines B. So, AG determines BG. If A determines B, then AG determines BG. That's the augmentation rule. It's like we just multiplied both sides by G. Pardon my abuse of notation here. I really should say we unioned both sides with a different set of attributes. The third one is the transitivity rule. If A determines B and B determines H, then A determines H. It's a chain of implications. So once you have the chain, the first link implies the last link. So A determines B, B determines H, therefore A determines H. The fourth one is called the union rule. So this is a means of combining two different functional dependencies whose left-hand sides are the same. If A determines B, and also A determines C, then A determines B and C. So the intuition is this. If a cause has an effect, but that same cause also has a different effect, then that cause actually has two effects. So this is called the union rule. And it has its own opposite called the decomposition rule. The decomposition rule is basically the union rule in reverse. If A determines B and C, then A determines B by itself, but A determines C by itself. The last one is called the pseudo-transitivity rule. If A determines C and CG determines H, if A determines C, then we can replace the C in the left-hand side of CG determines H with A, so we get AG determines H. This is from the transitivity rule, so it's called the pseudo-transitivity rule. So we have these 6 rules of inference. The first 3 make up what is called Armstrong's axioms, a set of axioms that we can use to reason about functional dependencies. These rules are sound, they don't generate anything incorrect, and these rules are complete. Given a set of functional dependencies F, those 3 rules alone are able to generate all of F+. F+ is the closure of F. F+, the closure of F, that is the set of all functional dependencies that we can make through inference alone. The rules are reflexivity, augmentation, and transitivity. RAT, RAT. Pretty easy to remember. The other 3 rules are derived from Armstrong's axioms. They don't make the rules of inference any more powerful, they just make them easier to use. Like how in relational algebra we had 6 fundamental operations, but then we defined several more just from those 6. Those 6 fundamental operations in relational algebra are enough. Adding new operations doesn't make it any more powerful, it just makes it easier to use. So, if we have a set and we want to find the closure of that set, is there an algorithm for that? Oh yeah, there is. It's a pretty complex algorithm though. So we repeat the following 2 loops here. So we repeatedly do these 2 for each loops until F+ does not change any further. So, for each functional dependency in F+, and we are going to start with F+ having all the same functional dependencies as f. For each functional dependency in f and f plus, apply reflexivity and augmentation rules on each rule, and then add the resulting functional dependencies to f plus. For each pair of functional dependencies in f, if that pair of functional dependencies can be combined using transitivity, add that to f plus. And we repeatedly do these two loops until we do not change f plus any further. There's another algorithm out there that lets us determine whether an attribute set B is functionally determined by another attribute set alpha. So like with the last one, we are going to set the result, which is alpha plus, to that of alpha. And we repeat this functional dependency. For each functional dependency, beta determines gamma in f. Determine whether beta is a subset of the result, and then union the result with gamma. And we repeatedly do this loop until the result does not change. So this second algorithm, as I said, is used to find that a set of attributes functionally determined by alpha under a set of functional dependencies f. So this is the closure of a set of attributes alpha. So if you have alpha, we can use this algorithm to determine alpha plus. In terms of time complexity, we're looking at a time complexity of on the order of big O of n squared. So let's do an example. Using those same functional dependencies as before, let's determine AG plus, the closure of AG. So here's our algorithm back in the top, and here's my face cam out of the way. So we have our 5 functional dependencies down here. We are going to start with AG plus only containing A and G. That is what this assignment operation is doing up here. Set AG plus to only contain A and G. Then we repeatedly perform this for each loop until we add nothing new. Let's begin with the first functional dependency. Is A a subset of AG plus? Is A in the result? Yes, so we're going to add B to AG plus. The formal way of describing is that we are unioning B with AG plus and assigning that to AG plus. It's a little bit more intuitive to describe it this way, so we're just adding stuff to the result. Though the proper way would be to say we are unioning it with the result. So now we just added B to the result. The next functional dependency is A determines C. Is A a subset of AG plus? Yes, it is. That means we also get to add C to the result. You see the pattern here? If the left-hand side of a functional dependency is a subset of the closure of the result, we add the right-hand side to the closure. Is C... So we have now CG determines H. Is H a subset of AG? No. Actually, no. I think I wrote that wrong. Yeah, I think I did. Is CG a subset of AG plus? Is CG in the result? Yes, it is. C and G, C union G, is a subset of AG plus. We're gonna then add H to AG plus. There we go. So now we have the next one, CG determines I. Is CG in the result? Yes, so we'll add I to AG plus. And then the last functional dependency, B determines H. Is B in the result? Yes, so we're gonna add H to the result. But we already have an H in there. So adding it again doesn't do anything. So the first time we do this for each loop, we added several things to AG plus. Now we get to do it again, because this algorithm does not terminate until the result does not change. So, back from the top. The first functional dependency is A determines B. since A is an AG plus, we add B to AG plus. But B was already in there, so it doesn't change anything. The same is true with A determines C. C is already in there, so we don't change anything. The same is true with CG determines H, CG determines I, and B determines H. Now we have reached the end of our for each loop, and in doing that, the result did not change, so the algorithm terminates. The closure of AG is ABCGHI. We can also try this algorithm here, but if we did that, the closure of F, it's gonna be a very large set. I had to ask AI to help me determine how large this set was, and it was at least 300 functional dependencies, and a lot of them were going to be redundant. So instead of just sitting down and walking through this algorithm, let's just play with the rules of inference and see what other functional dependencies we can figure out just by inferring them from F. So again, F is the set of 5 functional dependencies. We want to find several more functional dependencies that would be in F+. So F+, again, is a set of all functional dependencies we can produce using those 6 rules of inference. So by the transitivity rule, we have A determines B and B determines H. Therefore, A determines H, let's add it. We can use the union rule on CG. So we can use this union rule to combine multiple functional dependencies whose left-hand sides are the same. So we have CG determines H and CG determines I. Therefore, CG determines HI. We can add that. We can also apply the pseudo-transitivity rule, where we have A determines C and CG determines H and CG determines I, and CG determines HI. So what we can do is replace that C with A. So now we have 3 more functional dependencies. AG determines H, AG determines I, and AG determines HI. We also have the union rule that can apply to all the functional dependencies whose left-hand side is A. That means we can add the functional dependency A determines BC. We can also use the transitivity rule to add A determines HC from A determines H. Hold on. Okay, so we can add several more rules to F+ by considering the union rule being applied to all the functional dependencies whose left-hand side is A, so we can then add in A determines BC. We can also do that for... We can also add A determines HC from A determines H and A determines C. So actually, this is another type, but that should be the union rule again. But we can add them. We can use the augmentation rule to also produce functional dependencies. For a functional dependency, for the functional dependency A determines B, if we union both sides with G, so AG determines BG, that's also a functional dependency in F+, so we can add that. The same is true for the reflexivity rule, so we can then add, if we have A determines B, then we can add B determines AB. So, F+ is going to be a huge set of functional dependencies that we can infer, that we had inferred from an original set of functional dependencies. So F is a set of functional dependencies, and F+ is all the functional dependencies that we can infer from F. So in a database, if you have a set of functional dependencies that all hold on some relation, when you update that database, when you update that table, the system must make sure that none of those functional dependencies are being violated. The thing is, the set of functional dependencies F might be so large that it just takes time to test. Way too much time to test. The thing is, we can infer another set of functional dependencies that is equivalent to the original set of functional dependencies that is equivalent. That is not only equivalent to the original set, but is smaller than the original set. So if we can produce another set of functional dependencies that is smaller but equivalent, if we want to update the database, instead of testing the original set, we just test the smaller equivalent set, and it'll take less time. That smaller set of functional dependencies is called a canonical cover, denoted as FC. So we find the canonical cover of a set of functional dependencies to eliminate extraneous attributes and redundant dependencies. All this is to reduce the amount of work needed to determine whether a set of functional dependencies was violated during an update. And for a canonical cover FC, which was derived from a set of functional dependencies F, FC is a simplified minimal set that is equivalent to F, and each functional dependency in the canonical cover has the two following properties. 1. No functional dependency in FC contains an extraneous attribute. That's number 1. Number 2. The left-hand side of every functional dependency in FC is unique. So we have to also talk about the notion of an extraneous attribute, which is defined below. But I do have another definition here as well. So suppose you have a set of functional dependencies F, and you have in there a functional dependency X determines Y. So the thing is, you're going to have two versions of this algorithm based on whether the extraneous attribute is on the left-hand side or the right-hand side. So let's just say that X contains the attribute A, so A is on the left-hand side. If we take out A from X, we produce a new set of attributes called X prime. And now instead of having the functional dependency X determines Y, we have X prime determines Y. If we replace X determines Y with X prime determines Y, and it and the rest of the rules still implies X determines Y, then A is extraneous and can be removed. There's a similar, as I said, there's another rule for if the extraneous attribute is on the right-hand side. So, for a functional dependency, for a set of functional dependencies F, which contains the functional dependency X determines Y, and an attribute B on the right-hand side that is a member of Y, remove B from Y to produce the set Y prime, and the functional dependency X determines Y prime. If F with X determines Y replaced with X determines Y prime still implies X determines Y, then B is extraneous and he can be removed. I'm gonna go actually write this down on paint.net. So our functional dependency is X determines Y, but it might be easier to think of it as the following. AB determines Y. And for the other one, X determines CD. So X is a member of a set of functional dependencies F. So X determines Y is a member. So there are more functional dependencies than just X determines Y. So if A is extraneous, then we should be able to remove it and have the remaining functional dependency B determines Y and everything else in F. This and everything else should be enough for us to infer that AB determines Y. That's the left-hand version. The right-hand version is this. If X determines CD and C is extraneous, we can remove it and then have the rest of the functional dependency x determines D, and everything else in F, that should be enough for us to infer that x determines CD. You want a few more examples? Sure, let's do a few more examples. Let's say that... Okay, so let's go back. We have these two functional dependencies, AB determines Y, and X determines CD. Let's also say that we also have the functional dependencies A determines Y and X determines D, and they're both in F. So let's write them down. Let's write down A determines Y next to AB determines Y, and X determines D next to X determines CD. Okay, so now let's look at the left-hand version. AB determines Y, but A determines Y. If A is enough to determine Y, then there's no point to have B here. So we can eliminate B from this functional dependency AB determines Y, and then we just have A determines Y. So it's basically on par with eliminating altogether the functional dependency of AB determines Y. Just through reasoning alone, we're able to determine whether a functional dependency has an extraneous attribute. That's basically all we're doing. We are reasoning whether we need a attribute in a functional dependency or not. Let's try the right-hand version. If we have the functional dependency X determines CD, but we also have the functional dependency X determines D, if X alone is able to determine D, actually in this case, we would need to split this into two functional dependencies, but actually that's something that we can't do. So really this should just be split into two functional dependencies, X determines C and X determines D. So actually in this case, we would remove D here, because if we try to split this into X determines C and X determines D as the undo operation of the transitivity rule, we would get two copies of X determines D, which is redundant. So if we have X determines D and X determines CD, that actually means that D is redundant on the right-hand side of this functional dependency. We can cross that out, so now we have X determines C. We can still infer that X determines CD just by merging them through the union rule. I think I said transitivity rule by mistake. Anyway, if we have these two rules, we can still infer X determines CD just by unioning them together. And in the case of this one, because A already determines Y, it's redundant to add anything new here. So A, B determines Y is redundant. I think we need a little bit more information to be able to infer that A, B determines Y, though. Anyway, let's look at an example where we try to make a canonical cover of a set of functional dependencies. Let's try an example. So we have the following set of functional dependencies: A determines BC, B determines C, A determines B, and AB determines C. There's a two-step process to do this, and here are our functional dependencies over here. The first step is to merge all functional dependencies whose left-hand sides are the same. This is basically the same as saying we want all of our functional dependencies to have a unique left-hand side. If there are two or more functional dependencies that have the same left-hand side, this is get combined into one using the union rule. So you have A determines BC and A determines B. We can just combine them into one, and that is A determines BC. but B was already on the right-hand side, so it's kind of like we just remove A determines B. We can bring back A determines B because we can undo the union rule but using the decomposition rule and get back A determines B. So if you're worried about A determines B, just keep in mind that we can apply decomposition to A determines BC and get back our original rule of A determines B. Alright, now all of our functional dependencies have a unique left-hand side. We can apply more rules of inference to the remaining two functional dependencies, B determines C and AB determines C. Since B alone is enough to determine C, the union of A and B, A is extraneous information that isn't necessary to determine C because B alone is able to determine C. That means we can remove the A from A determines BC, which is basically the same as eliminating AB determines C altogether. So now we are left with two functional dependencies, A determines BC. We can apply the decomposition rule to get the two rules A determines B and B determines C. Now you have three more functional dependencies, and the rule that says each rule must have a unique left-hand side has now been broken. But wait, do you see the transitivity rule in there? We have A determines B and B determines C and A determines C. That's the transitivity rule. We can remove A determines C because we can infer it just from the remaining two functional dependencies. A determines B and B determines C, therefore A determines C. It's redundant to include A determines C since we can just infer it from everything else. Therefore, we can remove A determines C. And there we go. That is the canonical cover for our four functional dependencies. A determines BC, B determines C, A determines B, and AB determines C. If we have a relation schema whose functional dependencies are that, we can just test this one instead. Sometimes you're going to have a schema that has more than one canonical cover. So let's explore this example with the functional dependencies A determines BC, B determines AC, and C determines AB. Let's test out A determines BC. We're gonna try that algorithm that finds extraneous attributes on the right-hand side in a functional dependency. So either B is extraneous or C is extraneous. We don't know which one, and we gotta determine which one. What we can do is split it into two rules, A determines B and A determines C, which is technically A determines BC, but with one of the attributes removed. So really we have two options we can go. We can either choose A determines B, which means that C was extraneous, or we can choose A determines C, which means B was extraneous. Can we still infer A determines BC using the remaining rules? Let's try it. For completeness, let's just split all the rules by decomposing them using the decomp rule. Using all of these rules, can we still get back A determines BC? Can we infer A determines BC from all the rules we have left? Well, let's look at A determines B. We also have the rule, okay, so for the left set, let's look at A determines B. We also have the rule B determines C. So we can infer back A determines C. For the right set, notice we have A determines C, and we also have the rule C determines B. So we can basically bring back A determines B. So we did not add these back. Rather, these rules, A determines C and A determines B, we just inferred them using the rules of inference. And then, here's what we can do next. We can apply the union rule to A determines B and A determines C in the left set, and A determines C and A determines B on the right set. That means we were able to infer A determines BC in the left set using all the remaining functional dependencies, and we were able to infer A determines BC from the remaining functional dependencies in the right set. That means we have two options for where to go here. Since we were able to remake the rule A determines BC for both sets, it means we have two options for where to go with our canonical cover here. We can eliminate B on the right hand side for A determines BC, or we can eliminate C on the right hand side for A determines BC. So we have a choice to make of declaring A. It means you have a choice to make. Declare C as extraneous and have A determines B, or B extraneous and have A determines C. So, as I said, we have two ways to make a canonical cover here. I'm going to cut to the chase and show you what those two canonical covers look like, and here they are. A determines B determines C determines A, and A determines C determines B determines A. Thing is, the textbook says there are way more canonical covers than these two, and it challenges you to find yet another one. So, I'm going to have to end this slideshow here, and I think I'm going to have to save our discussion on fourth normal form for this week's later video. But before I go, I'm going to give you the details of your next homework assignment. So this one is a bit shorter than the last one, but if you have done homework 2, you are already like 90% of the way done for homework 3. Because you're going to take 4 of the queries from homework 2 and convert them into relational algebra expressions. I'll show you the details. Okay, so it's basically just one question with 4 queries. Find the names of all students who have taken at least one computer science course with no duplicates. Find the names of all students who have never taken a computer science course, again with no duplicates. For each department, find the max salary of instructors in that department. Assume each department has at least one instructor. And across all departments' maximum salaries, find the lowest of those maximums. So, if you recall, these are basically the first 4 queries from the last homework assignment. The only difference here is that you're not going to write the queries using SQL, rather you're going to write them in relational algebra. You are welcome to use any and all operations that we discussed in Chapter 6, regardless of whether they're a fundamental operation or a derived operation or an extended operation. Once again, here are all the schemas that you need to answer all those questions. Alright, so that's homework 3. If you need any assistance on this, I'm available on Wednesday for office hours, or you can just email me. And yeah, that is going to be this week's video that should have been for last week. I'm going to have to make another video for this week and post it later. But yeah, that's going to conclude what was supposed to be last week's video. Take care, and I'll see you next video.